Yeah. Yeah. Okay. Shh. Wow, it's like immediately. Boom. Talking just gets going again. All right. So let's unfold the top right corner of the page and continue reading where we left off. You know, like you dog-ear a page when you stop reading for a moment.
I got
Do you use a bookmark?
It's a metaphor.
I don't read.
What? If I were to read, I would probably
fold the page.
I do too. I don't like bookmarks. They're too bulky. You know what's actually ruining the book?
I'll read it, and then I'll stop reading, and I'll never pick up against it.
Okay. How many ATP are formed? 32 to 34. Excellent. Okay, so aerobic respiration generates 32 to 34 ATP for every what? I gave you the general formula for cellular respiration on Tuesday. For every sugar, typically glucose. Okay, and the reason why we use glucose as we go through glycolysis is not because glucose is the only sugar that can go through glycolysis. Why do we put glucose in when we do the formula for cellular respiration? Carrie. It is carbon-based. Katie?
It's the most common.
It is the most common. And then there are two cells in the human body that can only metabolize glucose, and they are, Emma?
Neurons and red blood cells.
Neurons and red blood cells can only metabolize glucose, which is wonderful because I don't know if you knew this or not, but you are not constantly consuming glucose, right? You have periods in between meals when you are not consuming glucose. You have a period at night where you're really not consuming anything. Unless you sleep, eat, which would be awesome, right? You go to sleep hungry and you wake up so full, and you don't understand how that happened.
And then all your food's gone.
All your food is
Like
gone,
someone robbed the house.
and you're like, I don't even know what's going on. Emma. There are many different causes of why somebody would sleepwalk, but ultimately it's parts of their brain are not being shut down the way that they should be. Yeah, Trinity.
My cousin eats candy in her sleep.
She eats candy in her sleep?
Who?
I feel like this is like one of those things where it's like she wants to eat candy in the middle of the night. She doesn't want to get, or she or he. She doesn't want to get in trouble for it. She's like,
She literally has like a bucket of candy on my lap.
I eat candy in my sleep. Mark.
At one point, like I was either like half awake or this was a dream, but like I ended up basically dreaming. I ended up taking some Hershey's Kisses from one of my cupboards, and then I hid them somewhere in my room, and then like I was either half awake or like dreaming, and then when I went over to that location, I actually found them there. I'm just like, wait a minute, did I actually take them?
Yeah. Katie.
Is it genetic? Because me and my brother, me and my brother both sleepwalk.
Yep. There is certainly a genetic component. All right. Shh. Bring it back. Bring it back. Lydia.
Oh, I'm sleepwalking. Like, how are people able to kind of like respond?
Because you're not actually in a deep sleep. Well, you can be in a deep sleep and be sleepwalking, I guess. Your heart rate's not going to be as low as what's typical in a deep sleep when you're lying down. But if you're having a conversation with somebody while they're sleeping, it's because they're in a light sleep. And so most of their brain is still working, but they're not fully conscious.
Slightly Emma question. But
Okay.
why is it dangerous, or they say it's dangerous, like wake someone up when they're sleepwalking? Why is that?
I think just out of like fear. Like you just freak out,
Oh, okay.
but I don't think it really is dangerous.
Can it like jumpstart their brain or their heart or something because like
That's what I
stroke
was
or a heart attack?
I was
Like
saying.
panic attacks. Like we accidentally woke up my brother one time when he was sleepwalking, and he just started like freaking out
Which
and
brother?
screaming and crying.
All right. So if we can focus back on chapter 9. Thanks. So on Tuesday we left off, I gave you the 3 steps of aerobic respiration. Step 1, glycolysis. Step 2, Krebs cycle. Step 3, oxidative phosphorylation. Now what you'll find is that there's actually a step 2A and a step 2B, and the Krebs cycle is more like step 2B, but anyways, that's for later. That's for later. We'll get there. Okay? So we left off here, right? And then I gave you the 2 steps of anaerobic respiration, and what are they? Yeah, Rick.
Glycolysis.
Glycolysis.
And fermentation.
Oh, yep. Glycolysis and fermentation. All right. So I think this is everything we had on the board from Tuesday. Yeah, Isa.
What is this?
This is cellular respiration.
Oh, okay. And what is it?
So aerobic is in the presence of oxygen,
Okay.
and then anaerobic is when oxygen is not available.
It's
Or oxygen may be available, but the organism can't harness it. There are some organisms that's the case. They live in an oxygen-rich environment, but they are incapable of harnessing oxygen. Okay, so aerobic respiration generates 32 to 34 ATP, depending on the particular tissue type. Okay, now of that, so here, what I'd like for you to do you have room after these to write some more?
A
little bit.
Okay, good, excellent. So glycolysis, of those 32 to 34 ATP, glycolysis generates 2 of them. 2 ATP generated by glycolysis. It's good stuff.
I'm not really carrying the load.
Of those 32 to 34 ATP, 2 more generated by the Krebs cycle.
So most of it is the oxidative.
Oh yeah. So that would leave 28 to 30 ATP if my math is correct.
Indeed it is.
And it is. It's not Monday. Have we talked about how I can't do math on Mondays?
No.
We haven't.
Okay. Which is so weird because Monday and math start with the same letter. Don't know if you noticed that
That's
or not. So you're like, oh, it's Math Monday. But this is not a good day for me. Alright?
Good job, Nick.
So 28 out of the 32 ATP is almost 90% of the ATP generated in aerobic respiration is generated in this last step. Okay? This is a lot. That is a lot. Alright, so now we go down to here. Look at here. How many ATP are generated in glycolysis? 2 ATP. Glycolysis is the same in both. And then in fermentation, how many ATP do you think are generated?
30.
30 to 32.
Okay, so we've got 30 to 32. How many people think it's somewhere around 30 ATP generated during fermentation? By a show of hands.
I feel like this is a trick question.
We've got 1 hand. How many think it's less than 30 to 32? How many think it's more? Oh, this is going to be fun. 0 ATP generated by fermentation.
That looks like
exactly what I
that.
said.
Or that.
0 ATP generated by fermentation, which means this process of anaerobic respiration generates how much ATP for every 1 glucose molecule? 2. Yeah, Mark.
Okay, I don't know whether you're going to end up explaining this or not, but then what's the purpose of fermentation?
Oh, I'm gonna explain that. You see this right here?
Oh, there it is.
Yeah, it's part of our agenda. We gotta talk about why does fermentation exist, and it exists for more than just making ethanol, by the way. Yeah, Michelle.
What does ATP do?
ATP, it's the energy currency of the cell. We talked about that before we went on break. It is the way that cells store and typically how they harness chemical energy is through ATP. The average cell in the human body makes and breaks 100 pounds of ATP a day. Yeah. Every cell in your body. I mean, it's kind of a big deal because I don't know if you knew this or not,
Classes when you say that straight.
but you have
Up to 4.
a lot of cells in your body. A lot. trillions even. And the average cell is making and breaking 100 pounds of ATP a day.
Wait, that's per one cell?
Per one cell. Every cell in your
wow.
body. Yeah, I know, it's a big deal.
How do you not weigh?
Because it's making it and then breaking it and then making it and breaking it. It's building it from material that's already there. And then as it breaks it apart, the material stays there. So it's no net change in mass.
Like +1 mass.
Yeah. All right. So this is cool stuff, right? You're like, all right, is that it? And it's no, of course it's not it, because we have to figure out how does this generate so much ATP? And it's because there are other products of these processes as well. So glycolysis, in addition to generating 2 ATP, glycolysis also generates 2 NADH molecules. Did you run out of space?
Yes.
I'm about
You
okay,
put a little asterisk and then go down, write that asterisk, and then fill in the rest, right? It's like a footnote. You guys know about footnotes.
We don't use them in a like
Just
format.
write inside.
But I know what you're talking about.
But you've read a book that had footnotes.
If I read
If you read books. Yeah,
I have read it.
I listen to books on tape, you know?
No, that's even worse.
You're like, I just kind of wing it, right? I just kind of wing it. All right.
I can't listen to the words.
So, the other thing that glycolysis generates that you need to be aware of is 2 pyruvate molecules.
Pyruvate?
Hey guys, pay attention to how much space is on the board when I write it, right? And then you know how much space you need in your paper.
There's always the same amount of space.
Use
No,
asterisks.
No, because your writing sizes are extremely inconsistent. Sometimes you'll write really big and like, oh, okay, we should write big. And then you start writing a lot of little things, and then it doesn't.
If I write it really big, it's because I'm really feeling it, you know? I'm really feeling it. You should put it big in your notes. All right, Krebs Cycle. Are you okay? All right, cool. All right, so Krebs Cycle generates 2 ATP. It also generates 6 NADH molecules. Oh boy.
Oh, bro, I'm out of break. Does that say pyruvate?
Pyruvate. It sure does.
But like,
I don't look at it.
Use asterisks and it'll still look good.
It's not touching on the bottom page, they're all together.
Yeah, I just should be then, you know?
That's exactly what it should look like. It's gonna be beautiful, Carrie. It's gonna be beautiful. All right. I mean, I'm not done. I've got more room here, so we're just gonna keep going. Plus 2 FADH 2.
Yeah, that's what
I've already done it twice.
Bro,
how about this? Just don't have OCD. Problem solved.
And that's
Watch this guy.
it for the Krebs cycle. Okay, that's it. I mean, we could put more, but we're not going to. We're not going to. Yeah. I mean, there's always more, but we'll be satisfied here.
There was a point in time where I had the Krebs cycle memorized.
Okay.
There's a point where
And yeah, Michelle.
Are you going to explain what does the
Oh, you bet I am. Yeah, don't you worry about that. Right now we're just doing our overview. You see it? Our overview. We'll get to all of those other wonderful things. Okay? All right. And so oxidative phosphorylation, you're like, we've got our 28 to 30 ATP here. Is there anything left?
No.
Oh, there is. We don't have as much room here, so I'm gonna write the same size. I'm gonna run out of space. I'll put it down here. You can do what you want for your notes.
Yeah, use
It's so. Oh man, it is. Okay, that's fine. I'm not afraid to use asterisks. It really warms my heart that you all worry about the appearance of your notes. I mean, that just. And then Rick's sitting here getting great joy from it, the same way that I get great joy from it. All right. So check this out. So oxidative phosphorylation generates 28 to 30 ATP. Also generates 10 NAD plus molecules.
What's the difference?
Because there's no hydrogen. So
There's no hydrogen.
charged.
Oh, that hydrogen went somewhere. Except for hydrogen is positively charged.
How does that work?
Oh, I'm glad you asked. We'll get there.
Also, you're calculating the N and the A. This shouldn't be like.
No, because it's not sodium. It's nicotinamide dinucleotide. Nicotinamide dinucleotide is what NAD stands for. Okay, so plus, look at this. Asterisk. And we'll drop this down here. Here's our asterisk. I'm not afraid, Tori. So here's our asterisk. There's more. So in addition to generating 10 NAD+, we also generate 2 FAD molecules. And I don't remember what FAD stands for. I'd have to look it up. I'm sorry. I remembered NAD. It's nicotinamide dinucleotide. FAD, I don't remember. Yeah, Trinity.
Are we done with the glycolysis?
Yeah. Oh yeah. I mean, for now, we're gonna we have to go back and talk about glycolysis in more detail. No. Not in our overview. Nope. Nope. Okay. And so it's like, cool. We're so close. But we're so close. But we're not quite done yet. Yeah, Mark.
What does it say on the at the edge of the board?
Oh, it's an asterisk. And then the asterisk is down here to continue.
Oh.
Yeah.
He's not afraid.
So plus, I'm not. And then plus 6 water molecules.
How does that make you feel knowing that
Look at
half
him.
of it
He
is
is
up
so
there
excited.
and half of it is
You know what?
He's never been happier. Look at his face.
On a typical day, I would feel nothing about having half of it there and half of it down there. But on today, it makes me feel incredible. I didn't say on today. What did I say? In today?
He said on.
Yeah, on today. Wait, does that not make sense?
That sounds weird.
On this day.
Yeah.
That's better.
Okay.
Today,
We're so judging, guys.
On this day,
We expect
Today.
nothing less than perfection.
Thursday, January 10th?
Yeah.
Oh my goodness, 2019.
January's flying
It makes
by.
me feel incredible because I feel like you thought it was going to bother me putting an asterisk and drawing down here.
He's unfazed.
But I'm unfazed, and the fact that I'm unfazed makes me feel renewed. Maybe
He has ice in his veins, y'all.
New year, new equal.
extravagant. Okay, and then
Vocabulary.
that's it for oxidative phosphorylation. That's all we're gonna put there. Okay. So we come down here, and this glycolysis is the same as this glycolysis.
Wow.
And so, in addition to the 2 ATP, what do we make?
2 NAD.
2 NADH and 2 pyruvate. Right?
Pyruvate.
I'm glad you asked. We'll get there.
It's on the board.
Oh shoot. Let's.
Maybe you're more observant.
Let me live.
So I know what you're thinking. You're like, what are we going to generate from fermentation? Because you've developed in me a hunger for this knowledge, Dr. Eagle.
Pyruvate.
Yes, Doctor.
Maybe and
Isn't it 2 NAD?
and I'm starving. Oh yeah, it is 2.
Is it 10?
Is that a mistake?
Yeah.
Not giving the amount of
You
something?
didn't recognize it, but we did.
That was your deal at
That was the
first.
second
Yeah. All right.
Now there's no way around
And
it.
it's in the recording, so we
There's
know.
one way or
Oh,
the
yeah,
other.
we heard.
You gotta take this one or you can take the last one.
Okay, for in preparation for Monday, make me a list of what you want.
No.
You don't have to do
Now I
it.
feel bad.
I'll take yours, Issa. All right. So, but here we are at fermentation. So we generate 0 ATP plus 2 NAD plus.
Wait, what?
This is what we're generating in the process of fermentation. 0 ATP, 2 NAD plus, and depending on the type of fermentation, okay, because in bacteria and yeast they generate ethanol. 2 molecules of ethanol. I will call this ETOH, which, here, I'll actually do it the right way. ETOH, 2 molecules of ethanol, which is why you use yeast to make wine, or to make beer, or to make any other beverage in which you need ethanol, because when they go through fermentation, they generate ethanol. We do not generate ethanol, which is good, because...
Would that make us like in a permanent state of like drunkenness?
Oh yeah, so when okay, so typically, ideally, our cells are doing aerobic respiration. Why?
Because oxygen's present.
Well, yeah, because oxygen's present, but why ideally?
Because we make more ATP.
Yeah, you get a lot more energy from your food molecules when you do aerobic respiration. But sometimes your tissues can't get enough oxygen to do aerobic respiration. Like when? When would you not be able to get enough oxygen?
When you're underwater.
Yeah, when you're underwater holding your breath, or if you're running, right, and your muscles are working so hard that they can't get oxygen fast enough, and they'll switch over to anaerobic respiration, and if your cells fermented ethanol in those processes, every time you ran, you would get drunk.
Runner's high?
Yeah, it's a little bit different, because you don't really call drunk a high. It's a depression. It's a depressant. It's not a stimulant. You know. Okay, so our cells do not ferment ethanol. Instead, so look at this. Hey, shh. Look at this. Pay attention. I'm gonna put a little slash here. So when you see a slash, you know it's either or.
Asterisk. Oh.
It's either or. It's not an asterisk. Now I've got space here. 2
Right on the wall if he has to.
lactate molecules.
Is there like a
Like in milk?
Yeah, it's a big hole.
is there like a shorthand version?
2 lactate is the process. Yes.
Is it true that like lactose intolerance isn't really like lactose isn't the issue? Like that most people are saying that they're lactose intolerant, but lactose like isn't.
Well, so there could be a number of issues that look like lactose intolerance. Yeah. I mean, you could have a dairy allergy.
It's like something else in the milk, like the process or something. It's not the lactose, but they think it's the lactose.
Some people, it really is the lactose, though.
Because they
Trinity and then Emma.
Is there like a shorthand version for lactate?
Is there a shorthand version? Not really. I mean, you can write out the molecule, but sometimes this is called lactic acid. Shh. The acidic version of this is lactic acid, and so when that acid builds up in your muscle tissues,
That's why you get sore.
that's why you get sore.
Oh, that's why
So-
you do cool down laps.
Yes, so this is what your muscle cells ferment when they are doing anaerobic respiration, is lactic acid. Okay? And then so, yeah, I mean, that acid starts to burn your tissues. Yeah.
That's not funny, but in track, we used to have like, I don't know, this is for hell week.
Yes, that's okay. Yeah, I think we're okay to talk about
Okay,
hell.
they're not-
Okay,
I
Trinity.
know. And it was always during spring break, and we would every day do like, we would do like 100-meter lunges 4 times, so our legs would be like rock hard because of all the
100-meter lunges? Oh, that is no joke.
It was horrible.
That is no joke.
We were all in good shape, so.
I was doing lunges the other day, and I maxed out at 4. 4 lunges, yeah.
I love lunges. They're the
I mean, it was pretty-
That's like,
I mean, they were 4 like textbook lunges, though. I mean, they were
Right now,
excellent.
right now.
you gotta
No.
get like 9
I'm not gonna do it in dress pants. I'd go to do a lunge and then rip my pants. It's not good. All right. So this is the end of our overview. So we can go ahead and we can come here, and we're gonna take that right off of our agenda. And so 30 minutes into the class, because this is now 2 minutes slow, or is it 1? 1 minute slow. 30 minutes into the class, we have knocked one thing off of our list of 7. Yeah, let's give ourselves a round of applause.
Improvement.
All right. Michelle, did you have a question?
Oh no.
Okay. Alright, are there any questions on our overview?
Yeah, can we not erase it?
Mark.
This is like sort of on topic, sort of off topic. But this would be like, what would be the difference between like being allergic to dairy and being lactose intolerant?
So if you're allergic to dairy, you are making antibodies against one of the proteins, typically in dairy products. And so, whereas if you are lactose intolerant, you can't digest lactose, so lactose accumulates and creates some discomfort and some issues. It basically messes with water balance, and so water will flow out of cells, and then if water flows out of the cells that line your intestines into your intestines, creates kind of an interesting, it creates like a water slide, right? Yeah, and then you can imagine where that water goes. But if you're making antibodies against one of the proteins in milk, you're going to have typically more than just dietary discomfort when you consume a milk product. Yeah. Yep.
Does it say ETOH?
It does say ETOH, which is short for ethanol. Alright, so there are no questions about the overview?
No, sir.
Okay, so we're going to talk about glycolysis in more detail, then we'll take a little lecture break. Okay? I'm going to erase this. Y'all have your asterisks in place.
I need that.
I swear, Tori.
I should.
No, Kyle would like not erase it. What was that?
Alright, so let's talk about glycolysis, shall we? So did you notice glycolysis is the only process that is present in both aerobic and anaerobic respiration, right?
Actually,
Okay, so let's talk about glycolysis. And let's do this. Let's answer it. Let's ask a series of questions. Okay? Look at this. What is glycolysis?
oh, God.
Rick?
It is the splitting of sugar.
Splitting of sugar. That is actually a wonderful way to summarize the what of glycolysis. It is the splitting of sugar. And what happens when you break bonds and split something?
Chemical reaction.
Yes, it is a chemical reaction, and what happens when we break bonds? It releases energy. And then the energy released during glycolysis is used to do what?
Move and do things.
Make ATP, which then can be used to move and do things, right? So what is glycolysis? It's the splitting of sugar. Another way to say this, so this is one way to answer it, we could also say this, the partial oxidation of sugar. Look at that. The partial oxidation of sugar. That's another way to answer the question of what is glycolysis. Okay? It's the partial oxidation of sugar. And I know you all remember this very clearly from your chemistry, your redox reactions, your oxidation reduction. And you remember the mnemonic oil rig?
Oh yeah.
And oil is oxidation is loss, reduction is gain, and we're like, what are we losing? What are you losing? Electrons. So loss of electrons. And so what that means then is during the process of glycolysis, we are stripping some of the electrons away from sugar. Okay? You love it?
Yeah.
Okay, good. One thing, yeah, I'm going to tell you this. I hope you'll remember it, and it'll be on the recording, so even if you don't remember, it'll come back to you. Okay. So I want to tell you something, and this probably will make sense to you. You can lose something without really losing it.
Yeah.
Okay?
What do you mean?
I'm gonna explain it to you. But so this loss of electrons, you may not actually notice a change in charge. Right? So you can lose electrons without. So let me explain to this. Okay? So I have a younger brother. He's 2 years younger than I, and he's still way scrawnier than I am. And so if I want to take something from him, I can still take something from him, but I'm a grown man and I'll just get it for myself. But anyways, when we were kids, my brother would get Christmas gifts, and it was really like me just getting 2 sets of Christmas gifts. Because I got what I got, which belonged only to me, and then I got what he got that really belonged to both of us, right? And so, in one sense, he would lose his gifts, but he didn't really lose them because I'm a gracious brother, so I would allow him to have time with his own materials as well.
You're a horrible person.
And so, sometimes this loss of electrons, it's not actually a loss, it's just you may be sharing them now with something that you can't share equally with. And so sometimes in the case of carbon, and we talked about this before when we talked about organic molecules, we talked about electronegativity. Do you remember talking about that?
Yeah.
And it's basically how strongly something attracts electrons to itself. And carbon and hydrogen have about the same electronegativity. So if you have something like this, CH4, okay? You don't need to write this down. I'm giving you an example. If you need to write this down, feel free. But so this right here is methane. And we talked about this also, that the reason why carbon is such a great element to build organic molecules out of is because carbon can make 4 bonds, right? So the way this actually looks is like this.
I knew that.
I also knew that. Okay, so this is what methane looks like. Each of these bonds represents what? We talked about this also, but it was before the break, and there's this whole half-life with information. What do each one of these lines represent? A bond, and what is going on in a bond? What's happening there? They are sharing 2 electrons. Okay?
2?
So, yes, every bond is 2 shared electrons.
As in like 2.
Yeah.
As in like 2 that are spending time around. Yes, at any given time, in this case, there's a high probability that carbon is enjoying one of those electrons and hydrogen is enjoying the other. Carbon and hydrogen have a very equal sharing of electrons. Okay, they'd be like maybe twins, right? So, I can imagine if I had a twin brother.
Hey, he's talking.
If I had a twin brother, I would not have outweighed him by 100 pounds like I did my younger brother. And still, no, it's not quite. It's about 80 pounds now as adults. Okay, so these are an equal sharing of electrons. But watch what happens here. Watch what happens here. You're gonna like this. Let's say this carbon, okay, gets basically transformed from being part of methane into carbon dioxide. Okay? So, let's just assume we've got a chemical reaction to carry that out, and we do. It's a combustion reaction, which is what cellular respiration is, and we talked about that on Tuesday, where you can take methane, you can burn it, and you basically convert that carbon from being part of methane into carbon dioxide. You're like, where did the hydrogens go? It's an excellent question. What's another product of a combustion reaction or of cellular respiration? Water. That's where the hydrogen go, right? Is it coming back? It's coming back, right? It's like riding a bike. But this is the kind of bike that it's not like I just get on and it's very monotonous, right? I'm just pedaling in circles. No, this is the kind of bike that you get on and you go like mountain biking in the most beautiful mountain range in North America, right?
Or you're out on a unicycle.
Okay, so now let's just play this game. Let's play this game for a minute. So this carbon, it was originally in methane where it's equally sharing those electrons. Now it's in carbon dioxide. And so carbon, it forms 4 bonds, and so it's going to form 2 bonds with each of those oxygens. Okay? And so it's still forming 4 bonds. Each of these bonds still represent what? 2 shared electrons. So this carbon is sharing 4 electrons with this oxygen, right?
Right.
And it's sharing 4 electrons with this oxygen. It is. So it's 8 total, just like it was 8 total here.
Yeah,
But oxygen has a much higher electronegativity than carbon and hydrogen do. Much higher. Oxygen is like I was as an older brother, right? Like people would give my brother and I shared gifts, right? It's like, this is a joint gift for you and your brother.
But it's just
Like a gaming system, or I don't think anybody got us anything else to share. Maybe when we were younger. But it's like a gaming system, right? It's like we're gonna share it. Basically, if I get tired of it, he can have it, right? So now this carbon, how many electrons does this carbon have here?
4.
8. 4 bonds. Each bond is 2 electrons. This carbon has 8 electrons. It actually has more than that, but we're just representing 8 in the bonds.
Is there 8 or 4 in the other one?
Every bond represents 2. So there are 4 bonds here, each representing 2. 4 times 2 is 8. There are 4 bonds here, each representing 2. 4 times 2 is 8. So this carbon has how many electrons? 8. This carbon has how many electrons? 8. So the carbon has not lost any electrons, but it has lost electrons. It's still been partially oxidized. Because it didn't actually lose electrons, but man, those electrons are spending way more time with the oxygen than they are with the carbon. So it hasn't lost them, but it's lost them. Just like my illustration, my brother didn't lose his Christmas gifts, but he lost his Christmas gifts, right? Mark.
It reminds me of a Christmas gift that I got, like this giant, like that technically me and my brother got. That was this giant, like Legos, like Star Wars.
Yeah.
But essentially, it's mine. Because due to the fact, for one, I'm the one who basically built the thing.
I get it. You're the older brother?
Yeah.
I mean, that's really, it's not because you built it. It's because you're the older brother.
I got a Baker Mayfield jersey for Christmas.
And you have no older brother to take that from you.
No.
But you have me, but
I have
I
my
wouldn't
older
take it
sister,
from you
and I
because
would
that's.
actually be concerned with her stealing it.
I have no desire
She has a Kylie
to
Jenner
have a
jersey.
Baker Mayfield jersey.
It's
Okay,
the
are you
brown
gonna get a Jalen Hurts jersey when he transfers to Oklahoma?
No, because
So
only
you
be
know
there
how you
for
were
a year.
saying that for your driver's test you drove a stick?
Oh yeah.
I learned.
You learned how to
That's the
drive a
one
stick
great
shift?
at it.
Man, I totally nailed it too. I drove a stick shift in a car that had no air conditioning in August. And so my instructor sat in the car and he's like, "This doesn't have air conditioning?" And I said, "No." He's like, "I would really love to fail you. Please help me." And I was like, "I can't do that for you, I'm sorry." And I gave him the ride of his life. And at the end of it, he's like, "You are the worst driver that I have ever passed."
Really?
He told me that, and I said, "That means more to me than you will ever know." And actually, my PhD advisor told me basically the same thing. He said, "You are the worst writer that I have ever passed with their PhD."
So you're
And I
like
was
the
like,
worst of the best.
"That means so much to me." I mean, he had only had 3 students actually complete their PhD, so I was the worst writer of 3. But I was like, that is that's powerful.
Worst driver who's ever passed.
All right, so we've got the what? Okay, so it's a partial oxidation of sugar, which means you should be expecting. During the process of glycolysis, you should expect to see some of your carbons being partially oxidized. So where maybe they used to have a bond with hydrogen, that bond with hydrogen is being replaced with a bond with oxygen. So you're starting to pull some of those electrons away. Okay, remember that. Store that somewhere. What about the where? Where of glycolysis? It does happen in the cell,
Great answer.
but we need a little bit more detail than that.
Lysosome.
Specifically, it happens in the cytosol.
Cytoplasm.
Well, cytoplasm is the material, cytosol's the location.
You're right.
Yep. So cytosol this is out in the cell. It's not inside of an organelle. It's out in the cytoplasm, in the fluid of the cell. So that's all we need.
It's out in the open.
You said cytoplasm.
Well, the inside.
Cytoplasm is the fluid, cytosol's the location. You can oftentimes we use them interchangeably. I hold you to a higher standard, right?
Yeah.
So most people will use those two terms interchangeably, but I want you to go, cytoplasm's the material, cytosol is the location, right? It's like the difference between the lake and water. Where you're like, well, where are you gonna go swimming? And you're like, I'm gonna go swimming in the water. And you're like, okay, but the water's the material, where's the location? You're like, I'm gonna go swimming in the lake, and then somebody's like, be careful for brain-eating amoebas that you can get from fresh water, and then you're like, oh, I can never swim in a lake again.
What?
I can't swim.
Okay.
Happy birthday,
Yeah, Naegleria fowleri. This has nothing to do with what we're talking about, but I'll write it so you can read about it. Naegleria? I don't know how to spell this properly. Naegleria fowleri.
What the heck?
Why? Your lifeguard makes you swim across the lake.
Okay.
Ooh, I like how that's spelled.
I think there might be an E somewhere here. I think it may be NAE or
Oh, I
NEA.
really like
Anyways, shh, guys, focus. Naegleria fowleri. It's a brain-eating amoeba. There are about 25 to 30 cases of it in the United States every year. 90% of them are in Texas.
Hey, I'm from Texas.
I am not.
Neither am I.
Okay, so when does glycolysis happen? And this is the beauty of it. Whenever there's fuel. Whenever there's fuel. And this will remind you that glycolysis can happen even if your fuel isn't glucose. As long as you're not a red blood cell or a neuron. Because they can only metabolize glucose.
They have a hard knock.
Yeah, although it's simple, because then you don't have to make as many different enzymes, which is great for red blood cells because they don't have nuclei in mammals.
When? Oh, yeah.
Okay, what, where, and when. We can do the how and the why. No, we're gonna do the how. We're not gonna do the why or the who. Yeah, Emma.
So I understand what the fuel is.
What the fuel is? Well, in our shh, guys. That's so rude to Emma. She asked a question. Does anybody even know what she asked? Well, Carrie and Katie, the two that don't talk, Trinity, you're sitting right next to her. Kyle, do you know what Emma asked?
Wow, you are terrible.
So,
Okay.
Emma wants to
When
know.
Emma asks questions, most of the time we don't have to
Okay.
listen.
What Emma asked was a really good question. She said, could you tell us what the fuel is?
Ooh.
Right? That is what she asked. And so in the equation that I gave you for cellular respiration, the fuel was glucose. Okay? Right? So this fuel can be glucose, and that's typically how you learn glycolysis. When we on Monday go through this again, but in way more detail, we're gonna deal with it with glucose, but it could be something else as well, but we've got to save that till our other, you see this one? Other fuels. Okay? So it's glucose or something else. Right? Okay. So now let's do the how. Can I erase all this? Because I need space.
Yes.
Alright.
Yes. That's what you get right. You're acting like the.
Wait, do you wait till he's completely done?
Yeah, because he be adding stuff like
Okay, I'll just put the how down here.
You can erase the what.
No, I won't. Okay. So the how. So we already know the what, right? It's a partial oxidation of sugar. We also know that the what is the splitting of sugar. Okay? So the how. there are 10 reactions catalyzed 10 reactions catalyzed by 10 different enzymes.
I know. Oh my god,
Your
it's
zeros are really messed up.
I know. They look like
They're really
reaction.
be-like.
They look like potatoes.
So like I like potatoes.
What you meant to use for harm, God will use for my good. Okay?
No, how it works is delicious.
Just go ahead and call me Joseph.
Okay. Okay, Jojo.
Y'all can put me into slavery, but you know what? I'm end up being in charge of Egypt.
You go, Jojo.
Thanks. Okay, so how this process of glycolysis requires 10 reactions catalyzed by 10 different enzymes. Okay? And you're like, oh, this is just awesome. It's just awesome.
You love science, huh?
I do. Okay, so we need more details because this isn't enough. Oh, we do. So reactions 1 through 5, right? There are 10 reactions. Do you see this? There are 10 reactions. This is reactions 1 through 5, and then we're gonna have reactions 6 through 10. 1 through 5, 6 through 10. I mean, how much are you guys enjoying today?
I usually enjoy most days.
Even if you don't spend them with me?
I enjoy those days less, for sure.
The days you spend with me?
I enjoy these days more.
Okay, good. Okay.
I enjoy
All right.
those days that I do not spend with you less than I do these days.
So in reactions 1 through 5, this is what happens, okay? Don't worry, on Monday you're like, I want to see every single reaction. We'll do that on Monday. Okay? So in reactions 1 through 5, we take glucose and we generate 2 molecules of G3P.
That's like a messed up version of RG3.
The projector's like blocking the bottom of the
RG3 post his ACL is a messed up version of RG3.
Now he's just Lamar Jackson's coach.
Okay, so reactions 1 through 5, you take glucose and you generate 2 molecules of G3P. There's the splitting, right? You take 1 molecule, you make 2, we split it, right? Look at that, the splitting of the sugar. But we haven't yet partially oxidized it, okay? So the splitting of the sugar, look at this. Kyle, I'm so happy I didn't erase this, because now I can go and add more stuff here. So the splitting of sugar, reactions 1 through 5. The partial oxidation of sugar, guess where that is? 6 through 10. Oh my goodness.
I told you, easy this.
You can fit that in there. You can fit, no problem. Fit that
No,
in
no
here.
asterisk.
Asterisks.
I can't say a plural.
Okay,
Asterisk.
we got this? 1 through 5, we take glucose, we generate 2 molecules of G3P. Okay? This, reactions 1 through 5, actually require energy. 2 ATP used. To carry out reactions 1 through 5, the cell invests 2 molecules of ATP. How many?
2.
2. Okay, so to get from glucose to 2 G3P, the cell actually had to invest a little bit of energy. It's almost like if you wanted to use the analogy of a single reaction to describe glycolysis, even though it's 10 reactions, but you wanted to do a single reaction to create an analogy for it, this is our activation energy. Right? You got to put a little bit of energy in to get energy out. Okay? So in 6 through 10, what do you think happens here? What do we have to start? No, we don't have glucose anymore because in steps 1 through 5 it's been converted. Yes! So 2G3P. And we are going to go to, what was our product of glycolysis? We won't worry about ATP just right now. We had 2 ATP,
2 NADH,
2 NADH,
Pyruvate.
and 2 pyruvate.
Did you skip all of them?
Oh my goodness! So in steps 6 through 10, we take our 2 molecules of G3P and we convert them into 2 molecules of pyruvate. And so in steps 1 through 5, we use 2 ATP, and overall in glucose, how many ATP do we generate? 2. But if we had to invest 2, we're in the negative right now. How do we get from -2 to +2?
You add 2.
No, -2, you add 2, you're going to be at 0. You have 3! Rick! You were doing so well today. To get from -2 to +2.
Oh, I thought you said
No!
positive.
+2!
I knew that.
4 ATP generated. 4 ATP plus 2 NADH generated. Let's say made.
Where's my pen?
Because generated is a longer word. Emma.
And we have an extensive
So for
vocabulary.
6 through 10, is that 2G3P? Does that come from the 1 through 5 reaction?
It does. Yep.
Okay. So
Oh,
it
yeah.
needs the other one?
Yeah, do you want me to erase this one and then just have the arrow?
No, I just wondered.
Okay. It does. Yeah, you can't do reactions 6 through 10 without doing reactions 1 through 5 unless you do something else. But we'll see that when we get to other fuels. Okay?
I know, right? We've only just finished, but how we done?
We're done with glycolysis. Let's just go
I
here.
feel like we're not gonna get to other fuels.
So that's it for that?
That's it.
I really feel like we're not gonna get to other
I mean, for now, don't worry though, because on Monday, we're not gonna be satisfied with saying reactions 1 through 5. Because I know what you're thinking. You're like, Dr. Engel, that's 5 reactions. Where specifically is that required? And the answers are, step 1 requires 1, you're not even listening. You're missing all of these nuggets of truth. Step 1 requires 1 ATP. Step 3 requires 1 ATP. Steps 2, 4, and 5 do not require any ATP. So you'll see that on Monday. All right? Okay? Any questions on glycolysis? All right. So we're going to take a little break. We're resumed. Let's do this. So the next one, we're actually going to do 2 together at the same time. So remember when I put the 3 steps of aerobic respiration up? I told you that one of those steps, we put it as step 2, but it's really step 2B. Because there's a 2A. And so we're going to take these 2 together. And we're going to say step 2A of aerobic respiration is pyruvate oxidation. Step 1 is glycolysis. Step 2A is pyruvate oxidation. Step 2B is what? The Krebs cycle, also known as TCA cycle, also known as the citric acid cycle. Love it! Okay? So now we're getting a little bit more detail here. So originally in our overview we put these as a single step. Now we're separating them out into 2 steps. Pyruvate oxidation. This is what happens during pyruvate oxidation. You take, how many pyruvate do we generate during glycolysis?
2, right?
2. So we're going to take those 2 pyruvate. Wow. Pyruvate. And we're going to work them through a 3-part reaction. It's actually 3 different reactions. But all 3 are catalyzed by the same enzyme complex. So I guess you could call it a 3-part reaction or 3 separate reactions. But we take those 2 pyruvate and we generate 2 molecules of what's called acetyl-CoA.
Wait, the arrow is a 3-part reaction?
Yes. So we take those 2 pyruvate, we go through a 3-part reaction to generate 2 acetyl-CoA plus, check this out, 2 NADH, okay, and 2 molecules of carbon dioxide. 2 acetyl-CoA plus 2 NADH plus 2 molecules of carbon dioxide. Okay, so now let's go back to the beginning. Vision the overview of aerobic respiration. And we start with glucose, yes? How many carbons are in a glucose molecule? 6, right? It's C6H12O6.
Yes, sir.
Okay? And then if we take that and we split it into 2 molecules of pyruvate, how many carbons are in each molecule of pyruvate? What is 6 divided by 2? 3. So pyruvate is a 3-carbon molecule. Okay? Does that make sense? We took one 6-carbon molecule, we split it into 2 3-carbon molecules. Okay? And then pyruvate, we generate 2 acetyl-CoA and 2 molecules of carbon dioxide. So how many carbons have we lost off of this? 1 each, right? We had 2 pyruvate, we formed 2 molecules of carbon dioxide. Okay, so each of these should be how many carbons in this molecule? 2. Each have 2, but there are 2 of them for 4 total. Okay? So when you look at this, when you look at acetyl-CoA, what you find is this acetyl group is this. And then there's attached to the rest.
Wait, I'm a little bit confused.
Me too. What are you confused about?
Okay, so the 2 pyruvate
Yes.
goes through a 3-part reaction
Yes.
and you get left with that?
Yes, you get left with all of this. So one of the reactions is going to strip a carbon atom off of pyruvate.
Okay.
Right?
So what is pyruvate?
Pyruvate's a 3-carbon molecule.
Okay.
Sort of a sugar. Like a really small sugar. So one of the 3 reactions is going to strip carbon off of pyruvate to form a 2-carbon molecule, right? One of the reactions is going to generate NADH, and one of the reactions is going to attach coenzyme A onto that acetyl group. So those are basically all 3 of your reactions represented by our 3 products. Emma.
So is it 3 separate reactions, each producing one of those products?
Yes.
Okay.
But see, this is where it's complicated because all 3 reactions are carried out by the same enzyme complex. So like they all happen at the same time. So is it really 3 separate reactions or is it a 3-part reaction? I don't know. I mean, you could really make a good argument for either. It is either 3 separate reactions or it's a 3-part reaction. Kyle. It's okay? Alright, it's okay. And notice we like NADH, right? We generated that during glycolysis. Something good. There's something good there with NADH. Okay? And this right here, this is as oxidized as you will ever find carbon typically. Okay? And notice it hasn't fully lost the electrons. I mean, it sort of has, but it still has the amount of electrons around its nucleus that it wants. It's just sharing them with a partner that's very, very selfish. Very, very selfish. Like my 7-year-old. Oh man, my 7-year-old is a tiny female version of myself.
Really?
Yes, because she shares with her siblings the way I shared with my brother.
That's funny.
Where it's like, if she's tired of it, you can play with it. Issa, did you have something?
Yeah. Oh, the law of order.
Lost her. Alright. Okay, so this is pyruvate oxidation. Notice, oxidation is what? It's a loss of electrons. And so these carbons in carbon dioxide are about as oxidized as carbon will ever get. So we oxidize 2 of the carbons, 1 from each pyruvate, forming carbon dioxide. Notice, what is one of the products of a combustion reaction, or of cellular respiration? CO2 and water. But this is where the CO2 comes from, at least some of it, not all of it. Alright? Is this cool for pyruvate oxidation? Because that's done.
Are you sure?
I am positive. I mean, until we come back on Monday and we're going to talk about things in way more detail. You don't like what?
It's like a giant circle.
With just one thing on the bottom? I mean,
Like, it's just odd.
Rick, chill. Just relax. It's going to be okay. Alright. So the Krebs cycle. The Krebs cycle takes two. What is it going to? This is 2B. What did we get at the end of 2A? We got 2-acetyl-CoA, we got 2 NADH, we've got 2 CO2. So the Krebs cycle can only start with some of those products. The CO2, that's going to leave. That's going to diffuse out of the cell. And then ultimately you're going to expirate it. Okay? The NADH, that's going to go to something else. So what this is starting with is the 2-acetyl-CoA. Okay, so the Krebs cycle is starting with those 2-acetyl-CoA. And what it ends up with, some of this we already put in our overview. Right?
Why is it minus? Like, what is that?
Oh, it's not minus, it's just showing it's bonded to it.
Okay.
Bound to it?
Yeah.
Bonded to it? I think both are correct. Bonded to it, bound to it. Bound is...
I think bonded sounds more like science.
Yeah, bonded is the correct science form. Bound is
Like
a...
English.
Yeah. Okay, so 2-acetyl-CoA, and what we generate is this. 4 carbon dioxide. Plus 2 coenzymes A. Coenzymes A? I think that is how you would actually say it. That's how you would have to pluralize it, but that sounds so strange. 2 molecules of coenzyme A. 2 coenzymes A. Gosh. I think that's how you would actually do it. So we generate 4 carbon dioxide, 2 molecules of coenzyme A, and then what else from our overview?
2 ATP.
2 ATP, 6 NADH, and 2 FADH2. That's it
It's
is.
making a lot of stuff.
It is making a lot of stuff.
There's not a lot of stuff to fuel it.
Just cranking its way around that wheel. Notice.
Wait, hold up. So only 2 of the acetyl-CoAs, like, make all that? Like, that's all it needs?
Well, each acetyl-CoA has, each acetyl group has 2 carbons, right?
Yeah.
Because the acetyl group looks like this. This is as reduced as carbon is going to get, right? Where it has as much electrons as it's going to get, because it's basically an even sharing with hydrogen. But these carbons are going to go from only being bound to carbon and hydrogen, an equal sharing of electrons, to becoming carbon dioxide, where they have a very unequal sharing of electrons. So in this process of the Krebs cycle, we are going to oxidize the rest of our carbons. But again, still it's a partial oxidation because they're not fully losing electrons, although it gets a little complicated when you're dealing with an entire molecule. But the individual carbons aren't really losing electrons, but they are losing electrons. Kyle.
So is that also a 3-part reaction?
It's actually an 8-part reaction.
Is it the same as?
Hang on, hang on. I gotta make sure that that's right. We've got.
Refresh from here.
Oh, don't worry. On Monday we'll get back into the Krebs cycle and we'll talk about all of the.
It's like a big circle, right?
It isn't. I mean, we represent it. We represent it that way, but it doesn't really happen in a circle of the cells.
And like all the things like start popping off.
I don't think it is. I don't think it is 8 reactions. I think it's 7. I think it's 7 reactions.
I just it's not the same as the 3.
No. These are separate reactions altogether. Okay? And then there's one more thing we need to do, and then we'll be done with the Krebs as well. Okay? So, is this okay? Does this make sense? The only thing we need to do is to say that 2A and 2B, they happen in the mitochondrial matrix.
That sounds really cool.
The mitochondrial matrix. Have any of you seen the movie The Matrix?
Yeah.
With Keanu Reeves?
Yeah.
Man, that movie was like the most popular movie when I was a kid. But I'm no longer a kid.
Is that the thing where it goes like?
Yeah.
Is this where
Yeah,
the
they plug them in order for them to go into the matrix, which is like a reality that's not actual reality.
You know what movie's good?
Yeah.
Yes.
Holes?
What?
Shia LaBeouf. It was one of his first films, if not his first film. Okay? Alright, and so now we're done with the Krebs cycle and pyruvate oxidation.
Wait, mitochondrial.
Yep, they happen, both of those take place within the mitochondrial matrix. So do you remember when we talked about the mitochondrion? The mitochondrial matrix has two membranes. The mitochondrion has two membranes. So it's not I'm not talking about a bilayer, all membranes are a bilayer, but the mitochondrion has two membranes. 4 layers, yep. So the mitochondrial matrix is inside both those layers. Okay, cool. Any questions? Alright, we're good? And look at that, now we only have 3 things left.
Can you go, the Naegleria fowleri?
Oh yeah, Naegleria fowleri, brain-eating amoeba. Yeah.
Yeah, you said that's in like all lakes or just
No, oh no. No, if it was in all lakes, we'd have way more than 25 to 30 cases a year.
Oh, that's good.
Oh, cases? Like it's like a disease?
Yes.
It's a parasite.
Oh, I thought it was thing. Maybe it's
Yes, ma'am.
You know, water bears are.
Oh yeah, tardigrades, moss piglets, water bears.
What do they do?
What did they eat moss?
Oh, is it really?
I mean, what did they do? I mean, they just kind of rock life.
Tardigrades survive in space.
They can survive in space. Yeah, so they actually took water bears. They took some water from off of moss where the water bears were living and eating and just rocking life. And they took it and they smeared it on the side of the space shuttle before it went up to the space station and back. And then when it came back from the space station, they scraped it off the side of, I mean, the water was gone now, clearly. But they scraped off of where they put the tardigrades and put them back into water, and they reanimate and just start rocking life again.
Don't they live forever, basically?
I mean, they're basically immortal. I mean, unless they get eaten by something. All right. Okay. Okay. So we have oxidative phosphorylation. Oxidative phosphorylation. And on Tuesday, I didn't put this back on today, but on Tuesday I gave you the alternative name for this. Oh, what was it? Electron transport chain. Okay, oxidative phosphorylation. This is accounting for very near 90% of all of the ATP produced during aerobic respiration. And in our overview today, it accounts for almost 90% of the ATP production. Right, between 28 and 30 of the 32 to 34 ATP are produced during oxidative phosphorylation. Okay? And so now we have to figure out what's going on. What on earth is going on? And we also call it what, Kyle? Electron transport chain. And what does that mean?
The electron.
We're transporting electrons from somewhere. We'll call this the start. Okay? So these are electrons. I'm going to abbreviate it like this. Electrons, here's where they're starting. Where they are going to end
It's like a board game.
is with oxygen. Okay, oxygen is going to act... Ladies.
She's being disgusting.
Okay.
These are great.
Okay.
This is the final part of the electron transport chain. This is why this can't happen without oxygen, because oxygen is what drives that whole process. Okay? And so what these electrons are going to do is go from where they start, and they're going to go down a series of complexes until they get to here, which will then make water. And you're like, that is so cool.
So good. So cool.
But we're missing something, because here we just have oxygen, here we have water. Where'd the hydrogen come from?
And how'd you lose an oxygen?
Oh, well, you would just make this.
Oh, well, that makes sense.
Yeah, so this is what the reaction is actually.
Do you want us to write that?
Yeah.
Do you want us to write that?
If you want. It's up to you.
So yes.
I mean, don't worry. Listen, guys, I don't want you to worry about getting all the details, because on Monday we're going to go back through all of these processes with like a huge amount of detail. It's like right now what we're doing, so everything we've done today, I'm just reading to you like the outline of this incredible book we're going to read on Monday.
Awesome.
Yeah. We're just I outlined it for you and I'm sharing it with you.
That's so stupid.
All right. So notice they're higher here than they are here. This is making you feel a little bit like maybe we should do this.
Did anyone else do that?
Oh, the shimmy?
Yeah.
Shimmy, shimmy.
It's not that I got sometimes you get a chill. I just got like the spirit moved within my soul. You know? A little charismatic.
It was like.
Okay, so here's energy. Look at this. Energy. And then here is time. And it's like these graphs we've seen before. Right? In chapter 8. And remember I told you chapters 9 and 10? They're like, so what? So what enzymes do these kinds of things?
They got it, yeah.
So what?
Who cares?
Look at this, oxidative phosphorylation. So the electrons are starting at a higher energy level, and they are dropping down to almost the lowest energy level an electron can be. And that's going to be when it's inside of a water bond. And you're like, why is that almost the lowest it can be? It has a lot to do with how water molecules are structured. So the electrons are dropping down in energy, and as they do, it fuels a very specific process. It fuels the active. Here, I'm just going to draw this. And we're going to reference back to what we did on Tuesday to represent our different transport mechanisms.
Yeah.
So what is this? Hydrogen is going from a place where this is hydrogen times 1 to a place where it's hydrogen times 10. It's going what? Is it going with the gradient or against the gradient? Against the gradient. Right? And what do you call a material being forced against its concentration gradient? Active transport.
That was gonna be my guess.
Active. It was gonna be your guess. There should be no guessing about it. This was.
Well, if that was my number one thing, I was like, that sounds like active.
This was 49 hours and 13 minutes ago.
Hours? 13 minutes?
Yeah, you gotta be able to hold on to information that long.
Well, no, because that was the first thing that came about. I was like,
That's way shorter than the half-life of knowledge.
but I wasn't like, that.
Okay. So these electrons are dropping in energy level. These electrons are dropping in energy level, and as they do, they fuel an energy-requiring process. Right? To actively transport something against its gradient requires energy. Right? Okay? And so what's providing that energy is electrons dropping from a high energy level to a low energy
So
level.
when they drop, are they releasing energy?
They are. That's being used to pump hydrogens across
It's like a
a membrane. So this membrane, notice here, hey, check this out. You see this here? The hydrogen are crossing a membrane. This represents the inner mitochondrial membrane. Okay, so hydrogens are being pumped across the inner mitochondrial membrane from the mitochondrial matrix, which is where steps 2A and 2B happened. Now they're being pumped against or across that inner mitochondrial membrane into what's called, wait for it, the inner membrane space. Because it's where? It's between the inner membrane and the outer membrane. And so it's called the inner membrane space. And so here, the hydrogens are being pumped from the matrix. Here's the matrix. Gosh, I'm feeling so good today.
You should really hide in your house. Did you have coffee?
I didn't. I haven't had coffee in...
Last time you drank coffee.
Well, before Thanksgiving, I had coffee on Thanksgiving Day, but before that, I haven't had coffee in like 4 years. No, that's not true. Yeah, because Dr. Phillips brought me a cup of coffee.
pH of caffeine?
Yeah, and then I drank it because I wanted to. So here's hydrogen ions are being pumped from the matrix into the inner mitochondrial. Oh no, inner membrane space. Let's just call it that. I know, Trinity, you said it, and so you can get the credit. Here. There you go. You get the credit.
Love that.
Yeah.
I like that a lot.
Okay? Is this awesome or what? And you're like, well, that's cool, but where did the ATP come from?
They come from the outer membrane space. Am I right?
No, because the outer membrane space is just the cytosol. Then you're outside of the mitochondria.
And that's
entirely.
where like glycolysis.
Okay, so what happens when you pump something against its concentration gradient? You set up a really, really steep gradient, right? Have any of you seen Cloudy with a Chance of Meatballs?
Kyle
Okay.
watches the movie like every day.
So it's a great film. So you've got all this food that doesn't get eaten, and they take over the leftover food eliminator, or whatever that machine is called, and it scoops up the food and then shoots it back behind that dam, right? And you create this incredibly complex status to where you have an enormous amount of potential energy, right? And then ultimately the dam collapses and then washes the cop and his family fully out to sea. Sorry if I ruined the movie for you. But I mean, the movie's like 8 years old, right? It's like, come on. Different time. It's so different. Like, you can't even compare the first and the second film. Oh, I've seen the second film.
There's a second one?
Yeah.
Oh my god.
I didn't see that.
They're so different. Okay. Shh.
Oh yeah, the strawberries all cute, and it's like.
Okay. Now you got me all lost. Oh yeah, so we've created, when we're pumping hydrogen ions against their concentration gradient, we're building up a lot of potential energy. Okay? A lot of potential energy. You see this? So this is hydrogen ions being pumped against their concentration gradient. In another place, and look at that, right to this 4H. I'm pointing right to that 4H in the equation. Man, this is great. We have a process called osmosis.
Oh, that's not nice.
That's Kimmy.
Whenever
Isn't
you say Kimmy, I think of
Kimmy Gibbler?
Yep.
Kimmie.
Yeah. No, K-A-M-M-Y.
I don't think it was a Y. I think it's an IE.
No, it's K-I-M.
Is it really?
But
That's
she's the type to
that's just awful. Okay, so here, guys, here we're pumping hydrogens against their concentration gradient using the energy provided by electrons dropping in energy. Here, we're allowing hydrogen ions to drop back down their concentration gradient through this complex right here. Do you see that circle?
Yeah.
Yeah.
Okay, that circle, I'm going to bring it over here. Okay, you see circle there, circle here, circle there, circle here,
Circle K.
circle there, circle here. Just put it down below it. Put it down below.
I'll put it to the side.
And this circle, listen, this circle is called ATP synthase.
ATP what?
Synthase. And what does synthase make you think?
Synthetic.
Synthetic, which means man-made. Synthesis, which means to make something.
So something's being made.
So when hydrogen moves back down its concentration gradient through a process called chemiosmosis, it moves through a complex called ATP synthase. What do you think that complex does? It makes ATP. It makes ATP. Okay? Oh man, we're not gonna. Who's Trinity? You said you don't think we're gonna get to other fuels? You were so right. We're not even gonna get to fermentation. But it's okay. It's okay because you guys are gonna be so well prepared for the AP exam. You're gonna walk in there. You're gonna remember all of the ridiculous things that I did and said in preparing you for the AP exam.
We have film sessions where we watch back the.
Okay. So let's go. Shh. Do you remember in our overview we said oxidative phosphorylation generates 20 to 30 ATP. It also generates water. It also generates 10 NAD plus molecules, right? And generates 2 FAD molecules.
Do you tell us
That was in our overview. What's that?
Do you tell us what NAD was? NADH?
NADH is hydrogenated nicotinamide dinucleotide.
I remember. Hydrogenated.
Yeah.
And you forgot the H. No, it's different.
No, because after it loses the H. Because these H's actually came from that. Watch this. So these electrons, where do you think they came from?
The NAD.
The NADH. Oh my gosh! So right here, you can fit this in. Don't freak out. There's room there.
No, there's not.
The electrons come from NADH and FADH2. Oh, there's room. There's room. I know you're thinking this. You're like, Dr. Engel, there's no room. There's room.
There's no room.
Just like you would think, listen, like Dr. Eagle, you've got 3 children, a wonderful wife, you already have a hamster, there's no room in your heart for anything else. But it's not true, we got a dog, right? We got a dog, and there's plenty of room in my heart. Yeah, we got a pool.
What's the weirdest animal you would ever consider owning? Like as a pet?
The oldest animal, I mean, I have a black widow spider as a pet.
Oh my god! Can you bring it in?
Yeah.
No! You're
Don't drink it. Can you bring it in?
Yeah, I'll bring it on Monday.
No, you
She's a good size. She's not enormous, but she's a good size. Wow, we're so close.
Did you catch her and just keep her?
Yes. Well, I didn't buy her. Why would I buy a? You can buy. I mean, you can buy anything you want.
Yeah.
But I'm not gonna buy a black widow spider when I can just go turn over a chair and find one.
What if it had like an egg sac, you know, and a whole bunch of babies?
Oh, she did have babies.
Oh my god!
But I moved her egg sac into a new container and then I let it hatch. And what happens if you don't allow the spiderlings to disperse? They start eating each other. And then eventually you start with, sometimes if it's a big egg sac, there could be 1,000 spiderlings that hatch from it. But then you end up with just one at the end. And it ate all of its siblings. Or it ate siblings that ate other siblings, but ultimately the organic material from all of the siblings end up in its body.
So you have 2 black widows.
Yeah, but then I let that one go.
No, you don't. The one like
Okay. So the electrons, listen. The electrons came from NADH and FADH2, and these hydrogens, where did they come from?
NADH.
The same place!
Whoa!
NADH. Oh gosh. Oh my goodness. I did lowercase a because break got me all confused.
Way to go, Rick.
And
I was just asking a
FADH2.
question.
The hydrogens came from there as well. So the NADH and the FADH2, they bring the electrons to the party. They bring the hydrogens to the party.
Bring the party.
And both the electrons,
The party and the people.
both the electrons and the hydrogens are necessary to generate the ATP. So you notice the the NADH we made during glycolysis, we made during pyruvate oxidation, and we made during the Krebs cycle. A total of 10.
Those are fun times.
The FADH2 we made during the Krebs cycle. And they come in. And so there's one last thing I'm going to give you before our time is up today, and I'm going to give you the ATP that each of those is worth. So NADH is worth, every one NADH molecule is worth 2.5 ATP.
That's a good currency system?
Yeah. I mean, everything has a value, right? And FADH2, every one FADH2 molecule is worth 1.5 ATP. Not quite as valuable as NADH.
1.5?
1.5 versus 2.5.
2.5. I thought that was 25. Oh, yeah.
No. No, but think about it this way. Okay, listen. Okay, we're running low on time, so we got to get this. How many NADH do we generate during glycolysis? 2. How many NADH do we generate during pyruvate oxidation? 2 more, for a total of 4. How many NADH do we generate during the Krebs cycle? 6, for a total of 10. What's 10 times 2.5? 25. How many FADH2 do we generate? The 2 from the Krebs cycle. 2 times 1.5 is 3. 25 plus 3 is 28. And the oxidative phosphorylation generates between 28 and 30 ATP.
So where did that one come from?
That's a wonderful question, which we'll address on Monday.
We're addressing everything on Monday, not tomorrow. Good luck.